This conference will now be recorded.
Hello, hello everyone. Today the topics will be Aufbau principle, Pauli's exclusion principle, Hund's rule, electronic configuration and its importance, how to write abbreviated electronic configuration, how to decide period, group and block, and stability of completely and half-filled subshell. So Aufbau principle, we'll start with this. In an atom, the electrons are filled in different orbitals according to this principle. Not only this principle, there are two more. One is principle, another one is rule. It is commonly known as Hund's rule. So these two principle and Hund's rule, these three will be required if we want to fill electrons in different orbitals. There, it is not that arbitrarily we can fill it in any orbital. There are some specific rules that we have to follow, and for that these three things we have to know. So first is Aufbau principle. When the atom it is present in ground state, that means the low energy state, then the orbitals are filled in the order of their increasing energy. So if you know what is that is the order of atomic orbitals according to increasing energy. First low energy, then it will be in the high energy atomic orbital. So we have to know this order. Once we know this order, we will be able to fill these electrons. So it means that electrons will first should be placed in the lowest energy orbital that is available. Then only the next higher energy orbital we should place the electron. Once the lower energy orbitals are completely filled, then only the electrons can enter the next higher energy orbital. And how you will decide that which orbital is having more energy than any other, that is dependent on n plus L rule, which we have already discussed. Fine. So here you can see, based on this n plus L rule, if you take different orbitals, for example 1 is 2s 2p 3s 3p, then just by adding the principal quantum number and azimuthal quantum number, you can get n plus L value. So as this n plus L value is increasing, energy of these orbitals are also increasing. So the first two orbitals 1s and 2s is having more n plus L value, so that is why it will have higher energy compared to 1s. But sometimes it may happen there is a tie. So for example 2p and 3s, you can see both are having same n plus L value, and in that case you have to choose that orbital as higher energy which is having higher principal quantum number. So among 2 and 3, 3 is higher, so that is why 3s will be having higher energy than 2p. Similarly, you will also see there are some more orbitals available where n plus L value is same. So you have to keep that in mind, that where it is same, you have to choose higher principal quantum number. Okay. Now these orbitals, as you have seen here, first 1s, then 2s, then 2p. Just move in this direction. 2s, then 2p. Now it is arranged normally in this way. So first it is 1s. So it is very easy to understand. See, just write 1s and below 1s in the same line write 2s 2p. Then the next line write 3s 3p 3d. That is the same principal quantum. The next line, all the orbitals possible with principal quantum number 4, 4s 4p 4d 4f. Now once you have written all this, just add in this order. That is, you have to move in this direction, then only you will be able to understand which one is having higher energy. After 2s it is 2p, and then after 2p it is 3s. So that is why you can see here we have 3s. After 3s it is 3p, and in this way it will move and so on. Fine. Now, though it is true, but one thing you also have to keep it in mind, that the order should be assumed to be a rough guide for the filling of electrons in the energy levels. Now, why I am saying so? Because sometimes it is observed that in many cases the orbitals are similar in energy, and small changes in atomic structure may bring about a change in the order. So under normal condition, obviously this is true. most of the cases, but there may be a few cases where this rule, you will see there will be some exception. So why it is so? Because just arbitrarily choose any of these. Suppose we have 4F and 5D. Okay, it is side by side. Though according to this rule, 4F should be filled first. But sometimes what happens? The energy difference between these two, it depends on which element you have chosen. That is also important. So sometimes it happens that the energy difference between these two consecutive, it is so low that sometimes the next higher energy orbital is filled first. That is, theoretically 4F should be filled first, but 5D is filled first. And you will see mostly those examples you will find in A block elements. But 90% to 95% cases, obviously Aufbau principle is followed. Next is Pauli's Exclusion Principle. This principle states that no two electrons in an atom can have the same set of values of all the 4 quantum numbers. We know that there are total 4 quantum numbers, and you have 2 electrons, any 2 electrons in the atom, and for these 2 electrons it is not possible that all the 4 quantum numbers are same. At least one quantum number must be defined, at least. So if we take example, we know there is a single electron in hydrogen atom, and the 4 quantum numbers, principal quantum number 1, azimuthal is 0 because it is s orbital. Then magnetic quantum number, only possible value is 0, and spin quantum number is half, right? But when we move to the next element, that is helium, now atomic number is 2. So for these 2 electrons, now what is the difference? Here also for these 2 electrons, principal quantum number, azimuthal quantum number, and magnetic quantum number, all these 3 are same. But the last electron, that will be, the last quantum number, that will be different for these 2. So for one electron, it is the same quantum number set that you have observed in the previous case, that is in case of hydrogen. And for the second electron, see here also n value 1, L is 0, M is 0, but now this one must be different. Okay, so this is this rule. If you write it in 1s, so one electron I am placing like this, and another electron, though this is 1s and n value, L value, M value all are same, but the last quantum number is different. So that is why another electron, that is the second electron, its direction will be different, because now it is minus half. So if you are writing this like both are in the same direction, it is actually wrong. It is not true, because if you are doing so, it means all the 4 quantum numbers for both the electrons are same, but that is not true. Fine. So as we know that spin quantum number can have only 2 values, possible values, so only 2 electrons, and that is the reason only 2 electrons can be accommodated in a given orbital in accordance with Pauli's exclusion principle. So this is for 1s. If you take 2s, then also you can place maximum 2 electrons. You cannot place number 3 electrons, because if you do so, then 4 quantum numbers will be same, and that is not possible according to this principle. Here we have this configuration. How many electrons? Here we have 2s 2 electron and 2p 6 electron. Total 6 electrons are there, right? So for 2s electron, we know for 1 electron n value is 2, L is 0, M is also 0. For the spin quantum number, for the first electron it is plus half, second one is minus half. Similarly, if you go to 2p, you will see, okay, let me, here L value is 1, because for any p orbital it is 1. N is 2. So these 2 are fixed for all these 6 electrons. But for all these 6 electrons, now ML value or M value, there are total 3 possibilities. Minus 1, 0, and plus 1. So under that is these 3, that is one is basically 2px, this is py, pz. Though it is not necessary that minus 1 will be always px, there is no such correlation. I'm just arbitrarily writing it. So for px, you can see under minus 1 m value, you can have two principal quantum, plus up, minus up. Similarly, for 0 m value, you can have two principal quantum number. For plus 1 m value, you can have two electrons. So that is the reason why in 2p, maximum 6 electrons can be present, not more than that. And if we follow this, so here this table is basically quantum number of electrons in the L shell. So here basically total 8 electrons. See, starting from first up to 8th, because here we have total 2s to 2p6, 2 electron in S, 6 electron in P. So total how many? 8 electrons. So for these 8 electrons, here we have in this table all the 4 quantum numbers. And if you look carefully, all the 4 quantum numbers are not same for this 8 electron. At least one must be different. Now n is same for all, it has to be, and L is 0 0 for the first 2 electron because it is S, but L is 1 for the next 6 electron. Similarly for S electrons, both are 0, but when it is P electron, there is -1 for 2 electron, 0 for 2 electron, +1 for 2 electron, and S value plus up or minus. Okay. So in this table, you can see all the 4 quantum numbers for all 8 electrons. Whose rule of maximum multiplicity? That is the last rule. Aufbau principle, Pauli's exclusion principle, and this is the number 3. According to this rule, each orbital in a sublevel of subshell, that is P, D, F, is singly occupied before any orbital is doubly occupied. It also, you can say it in another way. Electrons present in singly occupied orbitals possesses identical speed. Oh, okay. Actually, not in different way. I mean to say, there are basically mostly when you will see any book or any study material, mostly you will find the first statement, that is each orbital in sublevel or subshell. That is, suppose we have 2s and 2p. So in 2p sublevels, if we see like this. Now first, if it is p 2p6, just take the previous example. And how you will place all these electrons? It must be placed like this. First one, next one, then one. Once it is singly filled, then you can place the 4th electron here, not before. So you should not fill it like this. 1, 2, then 3, 4. No, it is not the correct way. First you have to place 1, 1, 1. Then you can place the 4th one, because you don't have any option. You have to place the 4th one in px. Fine. So each orbital in a sublevel or subshell singly occupied before it is doubly occupied. And there is another statement that you have to keep in mind here, that the electrons present in singly occupied orbitals, they should possess identical speed. So here you can see 2p6. Suppose if it is 2p3, or better you take this example. Here we have taken carbon as element, and for carbon, the outermost electronic configuration is 2s to 2p. If you write the full electronic configuration, it is like this, but we are interested only 2s to 2p. So 1s 2s, there is no problem, because there is it is fully fit. So you don't have to, that is, Hund's rule is not required. But when you are placing the 2 electron in 2p, what is the correct way that you have to remember? So if you are filling the electrons, suppose both the electrons you have placed in single orbital, it is not correct. Okay, cross sign is there. Now you have placed it singly. That is fine, but their direction is opposite. This is also wrong. Their direction must be same. So it is not enough that you are placing them singly. Obviously that you have to maintain, but that is not enough. You also have to maintain. You have to be careful whether their direction are towards the same side or not. Either you place both of them towards upper side, or both of them towards that is downward. But one is downward, one is upward, that is not correct. So that is why the first two configurations are correct and the third and fourth not correct. Now if I elaborate it, the first rule, we know there are total 3p orbitals, then 5d orbitals and 7f orbitals that we have seen in the last class. 3p because ml values are total 3, 5d orbitals because ml values total 5, 7f because ml values total 7. So that is why there are total 3p orbitals, 5d orbitals, 7f. According to this rule, pairing of electrons in this orbital starts only when the fourth electron for 3p, the sixth electron for 5d, and the eighth electron it is for 7f. Why it is so? Because 5d means what? There will be total 5 rooms for single electron. So once you have placed all these 5 electrons, now the sixth one you can place in the first room. Then the 7, 8 like this. Similarly, when it is 7f, there is basically total 7 rooms available. 1, 2, 3, 4, 5, 6 once more. And here, if suppose there are total 8 electrons, you have to place F8 electrons. So how we will do so? 1, 1, 1, 1, 1, 1. So 7 electrons are there. Now the 8th electron, it will be now, repetition will be there. So that is written in this rule. What about the second rule? The first electron in a sublevel could be either spin up or spin down, upward or downward. Once the spin of the first electron is chosen, now the spin of all the other electrons. In this case, we have only 2 electrons. So the spin of the second electron. But suppose it is more than 2. That is why in general I am saying, once the spin of first electron is chosen, is fixed, the spin of all the other electrons in that sublevels are basically fixed. So that is why, see, when I have placed all these 7 electrons, I have maintained the direction only towards a particular side. So you can do it upward or you can do it downward. But generally, what we do by convention, the first electron it is placed with upward arrow like this. Then the second one is also upward. Third one is also upward. Now once you are doing the pairing, that is repetition is started. Now it has to be opposite sign. And that is you have to maintain. Because if you are not maintaining, suppose if you are doing the pairing towards same direction like this, it is not correct, because according to Pauli's exclusion principle we have seen, for all the 4 quantum numbers cannot be same for 2 electrons. Okay, so you have to combine all these rules, then only you can write the electronic configuration. So now we will see electronic configuration, how to maintaining all these rules, how we can write it. So what is electronic configuration? It is basically the distribution of electrons in different orbitals, and how we will write it based on all these principles that we have just discussed. Electrons in the completely filled shell are called core electrons. For example, just take the previous example, that is for carbon. What you have seen? 1s2, 2s2, 2p, 2. So this is completely filled. So the electrons in the completely filled shell, that will be called core. So this you can call it core electrons, right? And these are valence electrons. So that is why valency of carbon is 4. The electrons that are added to electronic shell with the highest n value, that will be called valence electrons. So these 4 electrons are valence electron. I'm writing V here, and these 2 electrons are core electrons. I'm writing C here. C for core, V for valence. The electronic configuration is basically written in this way, NL6. So it is nothing new. Just see how I write it. 2s2 or 2p2 for carbon. So this is basically N. So it is N. S is L and 2. X is 2. So where N is principal quantum number, L is represent the later designation of the orbital. We know that later designation is S when L value is 0. Letter designation is small p when L is 1. Similarly, L for L equal to 2 and 3, it is D and F respectively. And X here is the number of electrons. So general format, if you see, it is like NLX. Now it may be 2s2, 2p2, or 3d5, 4f13, like this. So here we have some examples of some elements starting from carbon, that is atomic number 6, then increasing atomic number from carbon to nitrogen, 7 atomic number, 8, 9, 10, in this way up to calcium, that is atomic number 20. Atomic number is given in the second column. Electronic configuration of the elements, that is given in third column. Also there is another electronic configuration format which is given in the fourth. Now when it is very small atomic number, suppose 6 or 7, you can easily write this type of configuration. But suppose if atomic number is very large, in that case it is better you express it in the second format. Suppose take calcium. It is having very high atomic number. Obviously compared to carbon it is high. So writing it in this way, it is really difficult or it is time taking. So it is better what you will do, just choose the previous noble gas configuration. So just before calcium, what is the previous noble gas? It is basically argon. And for argon, up to this configuration, it is a full configuration of argon. That means up to this point, up to 3p6, you can write as if it is argon. So that is why what is written in the next column. So we have not written this elaborately. This part we have written as if it is argon. And then 4s2 you have to write. So if you express it in this way, it will be easier for us, less time consuming. Now it is, see, it is 20, but you may have atomic number even higher. Suppose it is 54 or 82, 83, then what you will do? Obviously, it is always better you choose the last noble gas, you write that noble gas, and rest of the electrons you have to fill according to all these rules. Above, Pauli's exclusion and Hund's. Fine. Similarly, suppose we have taken aluminium. 13 is the atomic number. What is the previous noble gas? This one, 10. That means after 10, 3 more electrons should be there. Now neon is up to 2p6. So that is why when it is aluminium, this part you can write as if it is neon configuration, and the other 3 electrons, it should be placed according to this we know Aufbau principle, because 3s after 2p6 it should be 3s, and after 3s it should be 3p. Remember Pauli's Aufbau principle, the first principle that we have started with which we have started the class, that I'm talking about that principle. So 3s2 3p1. So if you express it in this way, obviously it will be easier for us. So this element that we have written in the third bracket in the last column that you are seeing for all these elements, it is always the last noble gas. So if you take oxygen, the last noble gas is basically helium, atomic number 2. That is not present here, but we know atomic number of oxygen 8. The previous last noble gas is helium. So that is why helium we know it is 1s2. So this part we have written as if it is helium, then 2s2 2p. Though it is very low at simple 8 atomic number, you can write the full configuration, but it is better if you write it maintaining the second format. So electronic configuration that you have seen, but there is another way, another style that you can follow when you will write electronic configuration, and that is by using orbital diagram. Now obviously it has some advantage, and what are those advantage, how it is different, that we will see. So hydrogen we have seen, you can write it like this, or you can write by this square box notation of corresponding atomic orbit. So it is orbital diagram method, and it is NLX method that you have already seen in the last slide. But sometimes it is important to represent in orbital diagram. See boron 1s2, 2s2, 2p1. So how we have written it? Like this. Now, in this case, each orbital of the subshell is represented by a box and the electron is represented by arrow. Positive sign or negative sign is downward. Now this notation, it has some advantage over the first type format that you have seen. And what is this advantage? The advantage is, if you represent it in this orbital diagram method, obviously it will help you to understand all the 4 quantum numbers, right? Because when you write it in this way, now you can easily understand here ml value is -1, 0, +1. And also you can see the direction of the electron from which you can predict whether it is +half or -half. But if you write it in this way, it is not clear to us what is the quantum number. Maximum you can have the idea, yes, it is quantum number n equal to 1 or 2. Then L value for S it is 0, for P it is 1, that you can see. But if you also want to get idea about magnetic quantum number and spin quantum number, obviously this orbital diagram representation is better, and that is the advantage. Importance of electronic configuration. When atoms come into contact with another atom, it is only the outermost electrons of these atoms, that is, I'm talking about the valence shell electrons, that only interacts, not the core electron. Remember, carbon 1s2, 2s2, 2p2, 1s2 is core electron. It has nothing to do with that is, it will not participate in reaction. So that is why it is not important. Only valence electrons are important. So that is why for each element, if you know its valency, you can understand what will be its reactivity nature. Okay. So only outermost electrons taking part, or you can say interacting with other valence electrons of other atom. It helps to classify electrons in different blocks. So if you know the valence electrons, whether it is in 2p or whether it is in 3p, based on that you can understand which block it will be. Suppose if it is 4s2, obviously it will belong to S block. If it is 6p, it will belong to P block. If there is electrons in D, suppose 4s2, 3d5 or 3d6, if obviously it will belong to D block. So from this configuration, you can also understand to which block the element belongs. So it will help you, making it easier to collectively study the properties of electrons. So I am writing suppose two elements, two different electronic configuration. Just have a look in the electronic configuration. You can understand to which group, not just block, to which group it is present, that also you can know. To which block, to which group, that is its position in the periodic table, you will have some clear idea. And that is the importance of electronic configuration. Electronic configuration can predict stability, because an atom is least stable or most reactive when the valence shell is incomplete, and also when valence shell is half filled. Suppose p orbital, maximum capacity 6, but suppose if it is half filled, it is 3. Now this half filled configuration is also very stable. So if you can see the electronic configuration of the element, you can understand whether it will be stable or not. And if valence shell, if it is incomplete, obviously it will try to fill its deficiency. Okay, so if it is 2p5, it will try to capture one more electron so that it becomes 2p6. So that idea also we can get how it will be, how much reactive it will be. Elements that are having same number of valence electrons, they have similar chemical properties. And when valence electrons are same, basically they belong to same group, because their chemical properties you can find some similarity. So for example, nitrogen, outermost electronic configuration is 2s2 2p3, and in the same group, this is basically group number 15. So same group, the next element is phosphorus. Now for phosphorus, here also valence electron must be 5. So for nitrogen it is 2s2 2p3. For phosphorus it has to be 3s2 3p3. Similarly, the next element after phosphorus, that should be 4s2 4p3. That means it is maintaining same valence electron Only difference is principal quantum number changing, because you are jumping from second period to third period, from third period to fourth period. So obviously n value will increase, but format of electronic configuration is same. So that is the reason nitrogen, phosphorus, arsenic, and the other elements in the group 15, their chemical properties, there is some similarity. The most stable configuration are the ones that have full energy level. That means fully filled configuration. And that is why noble gases are so stable. They hardly take part in reaction. The noble gases are very stable elements, do not react easily with other elements. Only under special condition they can react. Electronic configuration can assist in making prediction about the ways in which certain element will react and what type of product these elements will produce by interacting with each other. Okay, so that also we can get some idea. So these are the importance of electronic configuration. How to write abbreviated electronic configuration? So we have seen we can represent it in orbital diagram method. I'm not talking about that. Abbreviated EC means we will write the previous noble gas within third bracket, and then the valence electrons that will be placed. That is the rest of the electrons after the previous noble gas that will be placed. But it is not full electronic configuration. We will write the noble gas, the previous noble gas, and then rest of the electrons will be placed. The standard notation often yields lengthy electronic configuration. Standard notation means you write the full electronic configuration. For carbon, it is 1s2, 2s2, 2p6. Fine. Now, especially when the elements are having very large atomic number, suppose 82, 83, like this. So in such cases, it is difficult to write. It will take a lot of time. So in such cases, it is better you choose abbreviated or condensed notation because that will be less time consuming. So now, what are the steps that you have to follow? It is very easy actually. Obviously, you have to know the first thing, that is must. You have to know the atomic number. Once you know the atomic number, suppose here I am taking one example, atomic number 83. Which element not required? Suppose it is 83 atomic number. Once you know this, you have to go back to the last noble gas. So basically, when you will write abbreviated EC, you have to know all the noble gases. So that is why in the right hand side you can see all the noble gases are written. Helium, which is from second period, neon, third, fourth. Sorry, it is second period is basically this one. Starts from here. 3, then 4, 5, 6, 7. So you just have to remember, there is no other option, you just have to remember this and obviously the corresponding atomic numbers. Helium, neon, argon, krypton, xenon, radon, OG, it is reactive element, is not required, and the atomic number 2, 10, 18, 36, 54, 86. Once you know this, then abbreviated EC for any elements you can write. So 83, what is the last noble gas? Obviously, it is not 86, it is more than 83. Last one is 54. That means you have to place xenon within third bracket, having 54 atomic number. Next step is that write the symbol of the noble gas in bracket to start the EC. Take note of the row in which the noble gas is present. Now, xenon is present in fifth. That means it is ending with 5s2, 5p6 configuration. So obviously the element that you have chosen, that will be in the next period, that is it must be in the sixth period because fifth period is already complete in xenon. So take note of the row the noble gas is present in the periodic table, and now you have to continue the rest of the electronic configuration. For that, you next step what you will do, what is the rest of the electrons? So 83 minus 54. How many electrons are present? It is 29 electrons. Now these 29 electrons you have to fulfill according to Aufbau principle. So that is why I have presented this Aufbau principle, this table that will follow. Now xenon is already ended at 5p6. Now after 5p, what you have? You have 6s. After 6s, what you have? 4f, then 5d and 6p. So after 54, you have to write 6s. Maximum capacity 6s, it is 2. After 6s, it is 4f, maximum capacity 14, right? After 4f, it is 5d, maximum capacity 10. And after 5d, 2 plus 14 plus 10, that means 26 electrons you have already covered. 3 more electrons needed, and that should be after 5d 6p. So it should be like this. Now if I write it, though according to above, 6s first, then 4f, then 5d, but 6p. But normally we write it in this way. That is 4f we write first. 6s is always placed just before 6p. That is the normally we follow. So 5d 10, 6s 2, 6p 3. So this is the electronic configuration of the atomic number 83. And from this, see, here you can see the principal quantum number is 6. It is from 6 period. So from this electronic configuration, even now you can predict what is the period. Period is 6. You can also predict the block. What is the block? The block is P, because the last electron is entering 3. So now you know the position. It is P block element. It is from 6 period, right? And if you know this, basically now you can see I have already placed here the P block 6. That means it should be this. It is Bismuth. Fine. Now in the next slide, we will also see how to decide period, block and group, because this type of question, or not just for this chapter, for any other chapters also, if you can from the atomic number you can easily find out what is the period, block, group. Obviously it will help you to answer different types of questions. If you want to know what is period, that we have already seen in the last slide. It is once you have written already electronic configuration by the rules that we have already discussed right just now. So there you have seen period is 6, the last element I'm talking about. So this is basically the principal quantum number, very easy to understand. So in this way you can decide period. How to decide block? It is nothing but the orbital which is receiving the last electron. So in our case, Bismuth last electron, it is in P. Suppose if it is in last electron is entering S, that is, just take the example of calcium, it is entering in 4s. So obviously it is S block element. So in this way you can also decide what is the block. How to decide group? That is the next question. Now for group, depending on what is your block, is it S, is it P, is it D, depending on that, 3 different rules you have to maintain. So once you know that it is S block or P block or D block, next thing that you have to do for deciding group, it basically depends on the number of electrons in the last shell, that is the principal quantum number, and n-1th subshell. So suppose the last electron is entering 4s, that is principal quantum number 4. So n-1 is 4 minus 1, that is 3. Fine. So when it is how to choose group, if it is S block, it is very simple. It is just the number of valence electrons. So for calcium, we know it is after argon configuration, it is 4s2. That means this number of electron, number of valence electron 2, that will directly give you the group number. So here group number for calcium is 2, second group element. If it belongs to D block, now what you have to do, you have to add the electrons that are present in nth shell and also the electrons that is present in n-1th shell. So I will take example of iron. After argon, it is basically, sorry, after argon it is 4s2, 3d6. That means 2 present in nth shell, 6 present in n-1. Just add these two, 8. So group number should be 8 and it is D block. Then for P, what you have to do, number of valence electron in nth shell plus 10. So just take the previous example. In case of bismuth, what we have seen, this is the valence shell, right? Now add all the valence electron, that means 2 plus 3. What you are getting? You are getting 5. Simply add 10. So bismuth is from group 15. You can also check it in the previous slide. Group 15 bismuth. Okay. So in this way you can decide. Here we have also taken another example. 54, then 14 plus 10 plus 2 plus 2, 4. That means it is 4, 18 plus 10. So it is total 28 electrons after 54. So atomic number is 82. So here you can see the valence electron total 4. So group number should be 4 plus 10. So it is 14. It is basically lead, atomic number lead. Fine. You can also find it here. Group number is 14. Group number 14, period is 6. So this is this one. 6 period. So now you know how to write electronic configuration, but basic thing you have to know the atomic number, otherwise you cannot write it. So if you want to write EC, electronic configuration, you have to know atomic number and also the above, according to above, which orbital is coming after which. You can also take the help of N plus L rule, and once you have written the electronic configuration, then you can easily decide period, block and group for any element. Fine. Here we have a question. Outermost electronic configuration of a group 13 element is given, which is 4s2 4p1. And it is group 13 that you can understand because it is p block element. Last electron entering p. 2 plus 1, total valence electron 3. If you add 10 with 3 for p block, you get group. So that is why it is 13. Now that is not the question. I was just saying. But what it is actually asking. Outermost configuration is given, group number is also mentioned. You have to find the electronic configuration of the element of p block period 5 placed diagonally to element E. So for E, this is the configuration. And you can understand from this configuration, it belongs to 4th period. Element E belongs to 4th period. That means, suppose if it is 4th period, 4th, diagonally, that means period 5. So the next period, 5th, its position will be somewhere here. If I am writing periodic table, its position should be somewhere here. Now, which electronic configuration in the options 1, 2, 3, 4 correct that you have to choose. Now, as it is 5th period and it is p block and diagonally, that means it is also the next group. Now, for this group, it is 13. The next group must be 14. 14 means configuration should be H2P2. Now, which S? It is 5S, 5P because it is 5th period, and 5S2, 5P2 that you can find only in last option. Okay, and even if you are not able to, suppose in 2 options, here it is okay, even directly you can reach it, but suppose in 2 options it is 5S2, 5P2, you also have to check the other part whether it is correct or not. So in this case it is okay, you cannot choose any other option, and even you don't have to look at which noble gas or 4D, though you can obviously check, but if you are in hurry, just as you know it is diagonally present, it is 5th period, and obviously total valence electron must be 4, though in all the options valence electron 4, 2 2 2 2, that is common. So as it is 5th period, it has to be the last option. Sorry, you can also check it. Group 13, 4s2 4p1. Now this is group 13 and 4th period 2 3 4. That means it is this one, gallium. So the diagonally the next group 14, it must be tin, and tin C 50, last noble gas is 36. That means after 36, 50 minus 36, these 14 electrons must be present. So 10 2 2, these are the 14 electrons. Okay, So that is all about this problem. Last option is correct. Now we'll see what is so special about half-filled shell and completely filled subshell, why they are so stable. We'll start with one example. Just take these two elements, both are from D block. Actual configuration for these elements, actually for some elements, here we have chosen these two. They slightly differ from the expected electronic configuration that is based on Aufbau. Remember in the first slide, Aufbau principle, when we have discussed, I have clearly mentioned you can find sometimes some exception. Okay, so now we will check that. The exactly half-filled and completely filled orbitals, they have greater stability than other partially filled configuration in degenerate orbitals. So see, for P, it is basically 3 electrons, then only it is half-filled. For D, half-filled will be when there will be total 5 electrons, 3, 5, and for F, it will be half-filled when there are 7 electrons. Because according to Pauli's exclusion, suppose if you are thinking why not place the 7 electrons here, no, you can't do that. Okay, first you have to singly filled. So that is why when F subshell is half filled, it is basically containing 7 electrons, F7. Now this can be explained, that is why, what is the reason behind it, why half filled subshell or completely filled subshell, they are so stable. The reason is symmetry, and main reason is basically exchange energy. Okay, so if you look at these two examples, chromium and copper. Chromium atomic number 24, copper it is 29. So if you wish, you can write it after argon. So up to this part it is basically argon. So after argon, what you have? You have 3d4 4s2, because argon is atomic number 18. It is 24. So 24 minus 18, 6 electrons must be present after argon, and that is according to Aufbau. It should be 3d first, then 3d4, sorry, actually it is 4s first, 4s2, then 3d4. Now this is expected, but this is not the actual configuration. Actual configuration is after argon, it is rather than 3d4 4s1, it is basically 3d5 4s1. Now why it is so? Because if you look carefully, if you place it like this, then d4, but if you are placing like this, it is 3d5, though it is 4s1, but it is 3d5, which is half filled configuration, which is stable because of exchange energy, and that is why this is chosen, not the expected configuration. Similarly, when it is copper, after argon, 10 more electrons you have to place, sorry, 11 electrons you have to place, right? So up to this point it is argon. The next 11 electrons, first you have to place it in 4s 11, that means 2, 9 more, so it is 3d9. So this is the expected theoretical configuration according to Aufbau. But as you remove one electron from 4s, and if you place it in 3d, it will be now 3d10 4s1. Now it is fully filled configuration. So that is why this is actual configuration, not this one. But what is the reason behind it? That is why half filled configurations are so stable. The first reason is symmetry. So see, just take P. We know there is Px, Py, Pz. It is true all of these orbitals they are degenerate, they are having same energy, equal energy, but their orientation is different. So when it is Px, it is according it is on x-axis, Py it is y-axis, Pz it is z-axis. That means when you are placing these electrons Px, Py, Pz, because of their different orientation, they will remain in different region. Now because of this symmetrical distribution, because if it is not symmetrical, it will be like this, Px, Py, Pz. Suppose you are placing 2 electrons here and here. That means both these electrons, their orientation is same. Though it is not true, I am just comparing. So when you are placing 1, 1, 1, all their orientations are different. So as a result, what will happen? The shielding of one electron on the other electron, that is relatively small, because they are not placed in same orientation. As a result, they will feel more nuclear attraction. That is, attraction from nucleus, and stability will increase. So this is the first reason. Second reason, exchange energy. When there are two or more electrons with same spin present in the degenerate orbitals. So suppose if you have carbon, these are the two electrons having spin towards same side, that means they are identical. Now this electron can go here, or the second electron can come here. They can exchange their places. So two electrons or more than two with the same spin present in the degenerate orbitals of a subshell, they can exchange their position because their quantum numbers are identical. Sorry, I mean to say their ml value is same, but spin number is spin quantum number is same. Only ml value is different. But they can exchange their position. There is no such problem. And when this type of exchange is going on, there is release of energy, and that is known as exchange energy. The number of exchanges, higher is the number of exchanges, that is maximum, better, more is exchange energy. And when this number of exchanges are maximum, when the subshell is either half filled or completely filled, then only exchange energy can be maximum. As a result, stability is also maximum. And this exchange energy is not only we are discussing here, it is fine, but it is, remember, it is also the basis of Hund's rule. Hund's rule, it says that there should be placing, we should be placing the electrons 1 1 1, then pairing should be there. Why it is so? It is because of this exchange energy. First it should be half filled, then the fourth electron for p you can make it a pair. So see, just take, suppose it is D5 system. In case of chromium, remember, it is either 3d5 or 3d4. Now when it is 3d5, this electron, it can exchange its position with all the 4 electrons. That means 4 exchange possible. Now come to the next electron, it can exchange its position with the other 3. It is already done, so we have fixed it. We are trying to see all the permutation combinations. Next, the third one. Now these 2 electrons we are done. Now the third electron, it can exchange its position with the other 2. So 4, 3, 2, 1. Total how many exchange? 10. But if it is 3d4, it is 3, 2, 1, 6 exchange. So it is obviously the first one is preferred. And how you will know what will be the exchange energy? You have to follow this rule. N into n minus 1 divided by 2k, where k is constant. Now n value, it is how many number of the singly occupied electrons are present. So when it is d5, n value is 5, that is small n. Don't think it is principal quantum number, don't be confused, it is simply n. So n is 5, that is because it is 3d5, and here n is 4 because it is 3d4. So for this type of configuration of chromium, exchange energy is 6k. But for this configuration, because this is not actual, this is actual. Now see, exchange energy is high, and this is the reason why this configuration is expected. Sorry, this is actual, though the previous one is expected, but this is not correct. Fine. Write all the 4 quantum numbers for all the electrons in 4f2. So in 4f2 you have only 2 electrons. Now for these 2 electrons, 4 is basically principal quantum number, f orbital azimuthal quantum number is 2, and 2 is the number of electrons. Now for these 2 electrons, 2 different set will be there. So for this principal quantum number 4, so sorry, L is 3. So D is 2, L is 3 for F. Now the possible ml values, as there are total 2L plus 1 and L value is 3, that means 3 into 2 plus 1, total 7 values. So these are all the 7 values of ml, right? So for the first electron, you can place it like this. So it is -3, -2, -1, 0, +1, +2, so one more will be there, +3. So the first electron, we generally follow this convention. First electron we are placing here. The second electron, only difference is now it is having ml value -2. So see, for the first electron it is 4 principal quantum number. These two will always be same for these two electrons. Only ml value will change. And as we follow this, that is -3 first, then -2, then -1. So that is why this should be the set of quantum numbers. Last question, which is the stable electronic configuration, nickel 2 plus or Fe3 plus? But for that you have to know, for neutral nickel atom, neutral iron, what is the atomic number and the corresponding electronic configuration. For nickel it is 28, for iron it is 26. So for iron 26 atomic number, you see how you can write, it is up to this point argon, then 4s2 3d6. But when it is Fe3 plus, 3 electrons lost. First electron is lost from 4s, that means it is 4s0 now. One more electron will be lost from 3d. So this is the configuration for Fe3 plus. You can also write it in this way. For nickel, atomic number 28, that means after argon, atomic number 18, 10 more electrons should be there. So 4s2 3d8. But when it is nickel 2 plus, 2 electrons will be lost from 4s. So that is, it is 4s0 3d8. Now just compare these two, 4s0 3d8, 4s0 3d5. We know half field configuration is always stable. So that is why the configuration of Fe3 plus, that will be stable compared to Ni2 plus. Okay. So we will end here. We are at the end of the session. Thank you for listening.